Good morning, Luca and Joel. 8th of June now, still in the middle of polar coordinates. Another week on this at least. I mean, I want to set you the assignment at some point, but that'll probably be set on Wednesday and then due by the following Wednesday or something like that. So, and then we'll probably review that a little bit before we move on to our last topic of the year, which is going to be de Moivre's theorem, a complex number topic. But let's get back to the present, which is polar coordinates. So far we've looked at how, what they are, how they relate to Cartesian coordinates and how polar curves relate to Cartesian curves. And we've also had a little look at how you sketch them and the idea of a tangent to the curve at the origin, which is an important concept for what we're going to be doing today, which is the area enclosed by a polar curve. Now, a lot of what I'm going to say you might know already if you've read the notes that I gave on last lesson, put in the the assessment for last lesson. So I want you just to read those in advance of today. If you haven't read them, you definitely need to read those as well as what I'm going to explain now. But I'm going to do it not from the notes, I'm just going to do it from my head. So let's just go over the concept so you can understand what's going on here. So if you have an origin and an initial line from the origin, then you can set up a polar curve by coming up with a relationship r equals f of theta, where r is the distance you are away from the origin on an angle of theta relative to the initial line L, and f is the thing that tells you the value of r for each of the values of theta. So I don't know if that made any sense. So and it can be all the way around. It can even go around more than once if you set your values for theta beyond 0 to 2 pi or minus pi to pi. You can set it for larger values and get things like spirals happening and that sort of stuff. Anyway, let's not worry about any of that. Let's just say that for our purposes, it's minus pi is less than theta is less than pi, a full circular set of values. Now this is just generic, so I'm just going to pretend the curve looks something. Oh, it doesn't really matter. Let's go. Whee! There we go. So just generically, let's suppose our curve looks like, it won't look like that. Let's suppose it looks like that. Okay. And you might be interested in how much area is taken up by the curve. So how much area is inside the curve. Well, before we think about the whole curve, let's think about a section inside the curve and how we might actually find out what the area of that is. So if, let's suppose, for example, that I set a value of theta equal to alpha. So that there is alpha. And I set another value of theta set to beta. So all the way to there is beta. So I've got this on an angle of alpha and this on an angle of beta. By doing that, I can... Oh, I've got even colours on me. Oh, there's even Mrs. Draw. No. Oh yes, hang on. There we are. So I might be interested in finding the area in there. Okay. Now, suppose I haven't got to A level yet, and I don't know what integration is. I don't know what differentiation is. I don't know any of those fancy dancy things. And I'm just going to use my basic GCSE maths to find an estimate for the area inside that section there. One method I could use would be to split this area up into sections and pretend that each of those sections is the sector of a circle of a certain angle. If that makes sense. And the radius of those circles is the distance I am away from the origin. Now obviously this is a bit of a fudge, because if I do put up a little section like that, okay, so suppose I'm interested in finding the area, that black bit there, then that might be, for example, over 10 degrees. Let's go back into degrees for this to make it a bit easier. So that might be 10 degrees. And this value here might be the radius that I'm going to use for that section. Now, to find the value of r, if it was that one I was doing, I would have to put my value of alpha into this function, and I'd be able to find a value for that radius there. And then to find the area, that I could simply use 10 over 360 times pi r squared. I acknowledge the fact that this line here would not be r, it would be something different, because obviously it's a different angle. It would be alpha plus 10 degrees that I'd be subbing in there, and I get a different value of r. So this isn't really a sector of a circle. This isn't even on a circle necessarily. It's a little bit curvy like a circle though. Okay, you can probably already work out where I'm going with this. I don't know. So anyway, if you were doing it at GCSE, you'd have to do that several times to get an estimate of the area in there. So what you'd effectively be doing is finding the sum of the areas of these sectors. You'd be finding the sum of each of the sectors. Now, if I was working in degrees, that would be theta pi r squared over 360. If I'm working in radians, and I think you've done this quite recently, you'll know it's a much simpler formula that you use, because the pi's kind of already been taken into account in the way that radians are measured, and the formula just becomes a half r squared theta. I think you've done that quite recently. So I would be summing all the individual sectors, which would each be found by using a half r squared theta, where theta is the angle for each of the sectors, and r is the radius of the sector, except it would only be the radius of one end of it because it's a bit of a fuzz. This would be an estimate of it, okay? And I would do this for values of theta between alpha and beta. It's a bit difficult to actually set this up properly. So it would be alpha to beta. It would be the sum of those, and I would have to choose how many of them I was going to do. So from that, you can't see. I'm not doing every one. I'm doing it. Say I'm going to do it 6 times. It needs setting up properly, but you get. I think you get the gist. I'm not making myself that clear on that. Anyway, I'll just get to the point. If you know anything about integration, you will understand that what it actually is a replacement of this with the perfect case, where you don't just have a set number of sectors, you have an infinite number of them. In other words, it's doing this to the extreme, where the number of sectors that you choose between alpha and beta is actually a lot, or more specifically, an infinite number of them. So this formula becomes the integral from alpha to beta of a half r squared d theta, if that makes sense. Okay, I know I've gone wrong now. This isn't alpha and beta at all, really, is it? It's quite hard to explain. This theta here isn't actually one of these values. It's the difference between that value and the next value, if that makes sense. Oh, you know what? I've started the video and I can't be able to explain it any more carefully than that. But that theta there, I suppose if I'd used d theta, it would have made more sense. It's actually how wide each of the sectors is. It's a bit like if you do trapezium rule, it's like the strip length, the h value, if you know what I'm talking about with this trapezium rule. That makes more sense. I've muddled that up a bit, but I'm not going to go back because it's not important. Okay, what's important is that that formula leads to that formula there, alpha beta a half r squared d theta, and that is what you use to find the area enclosed between two different angles for a curve. Okay. Right, let's do an actual example and it might become a little bit clearer to you, and I can also make another couple of important points. So I've come up with, I haven't looked at the notes, so I don't know if this is in there, so I've come up with this one. Suppose you have the curve r equals 1 plus 2 cos theta, okay, and you're running that between minus pi and pi, so a pretty typical polar curve. What does it look like? Well, you did sketching last lesson, so I'm sure you could find this out for yourself. But it does actually look like this. Okay, first of all, if you put a 0 in there, then that's going to be 1 plus 2, so that's going to be 3. So it's going to come out to 3 here. Okay, if you put a pi over 2 in there, 90 degrees, it's going to be, oh dear me, I'm very tired. If I put pi over 2 in there, that's going to be 0, so it's going to go up to 1. We'll get there in the end. And if you put 180 degrees in there, that's going to be minus 1. So the overall value of this is going to be 1 minus 2, which is minus 1. Now minus 1 is not allowed according to the way we do this. So presumably somewhere between pi over 2 and pi, 90 and 180, it must have become 0 in order for it to go negative. To find where that is, we would need to solve the equation 1 plus 2 cos theta equals 0. Or in other words, cos theta equals minus a half. Okay, so you can do that with a CAS diagram or whatever method you use, or your calculator or whatever, but if you do that, you'll find out that theta is equal to 120 degrees or 240 degrees in old money. Now 120 degrees is going to be 2 pi over 3, and 240 degrees is going to be 4 pi over 3. So those are the two values of theta in radians for which r becomes 0. And they're important because they tell you, if you like, the tangent. So this is 120 degrees here, I'm a dotted line, which the curve comes into the origin on. So if I draw this, it's going to look something like this. This is very rough. Oh God, it's very rough. Like that. I'm not sure it's supposed to bulge out quite like that. That's rubbish. I'm sure. Just slightly take my bulge out there. There we go. That's better. Okay. And if you find the other tangent's the 4 pi over 3 one to 40 degrees, and it's actually going to be symmetrical. There's actually a rule that explains why any polar curve for which the theta appears inside a cos function will always be symmetrical about the initial line L. So that will be a line of reflection. I'm not going to go into that now. Anyway, there is the curve. Okay, and we are now going to find the area inside that curve using this new formula here, which I kind of try to explain where it came from and made a bit of a mess of it, to be honest. But hopefully you've got something out of my my explanation. It's quite difficult doing it when you're recording a video, if I'm honest. So there we are. We are now going to find the area enclosed by that curve using the formula. So the formula is, so the area I'm after is equal to the integral between, now it's going to be between, well, in general, it's alpha and beta, a half r squared d theta, like so. But in our case, it's going to be minus pi to pi of a half, open bracket, 1 plus 2 cos theta, all squared d theta, like that. So I have subbed in for r the function that makes the curve 1 plus 2 cos theta. And I'm ready to go. I just need to evaluate that expression there. So let's go about doing that now. So first thing I would probably do is just take the half outside for now. It's going to get in the way otherwise. And I need to multiply. I can't integrate that directly. I need to multiply it out. So it's 1 plus 4 cos theta plus 4 cos squared theta, like that. Okay. Now, I can definitely integrate that. However, I cannot integrate cos squared theta. This comes up all the time with polar coordinates because often the function f of theta that makes the curve is cos theta or sine theta, or something to do with cos theta or sine theta. So by the time you've squared it according to the formula, you're going to end up with a cos squared theta term. And you're going to need to integrate it. And it doesn't integrate. You won't find an expression for it in the formula book. However, I don't know if you've read the notes yet from the last video. But in order to actually do it, you have to use a trigonometric identity. I think Joel was asking me about this identity for the previous lesson last week. So I'm just going to tell you what that identity is. It's a double angle identity for cos 2 theta. It turns out, or it can be shown, by using something else called the addition formula, which I don't think you've done yet in normal maths. Cos 2 theta is cos squared theta minus sine squared theta, like so. Okay. Now that particular version of it isn't a lot of good to us, because if I rearrange that and use that to eliminate cos squared theta from here, I introduce a sine squared theta, which is just as bad. So I need alternative versions of this. Unfortunately, there are two alternative versions of this, which are easy to derive from using the identity from last year, that sine squared theta plus cos squared theta equals 1. 3 fingers on it really, shouldn't I? I should there as well, but it doesn't matter. So how do you use that to change this identity? Well, you use it to eliminate either the cos squared or the sine squared. Okay, and if you eliminate the sine squared, you will end up with 2 cos squared theta minus 1. Try it for yourself if you don't believe me. And if you eliminate the cos squared theta, you'll end up with 1 minus 2 sine squared theta. So we have these 3 different versions of the same trigonometric identity. The one that you derive first when you're proving the result, and then the 2 that are derived from that, which are actually useful to us. So it's these 2 fellas that we will be using whenever we have to integrate sine squared theta or cos squared theta in one of these polar area questions. So in this case, the one I actually want to use is the first one, but I need to rearrange it first to make cos squared theta the subject. So if I do rearrange it, I get cos squared theta is equal to cos 2 theta plus 1, all divided by 2. And what I'm going to do now is I am going to sub that in there. Easy. Let's do that then. So if I sub that in there, I get 1 plus 4 cos theta plus, now it's over 2, but I've got a 4 in front, so if I combine those together, that's going to give me 2 lots of the top. So I'm going to get 2 cos 2 theta plus double the 1 is 2. I hope that made sense to you. Okay. Now I'm going to be integrating now. If I was being less lazy, I would now have another line where I'd put those and call it 3, but I'm not. You just got to imagine in your head that I've written that line and I've now got 3 there. You'll need to imagine that, because otherwise it won't make sense why Sir is suddenly writing 3 theta here. I'm writing that because that's me integrating 3. And the integral of 3 is 3x, or 3 theta in this case. The integral of cos, can you remember? Well, the differential of sine is cos, so the integral of cos must be sine. So that must be 4 sine theta. Okay. Now, the integral of cos 2 theta is sine 2 theta over 2. So I'm going to get plus sine 2 theta over 2, but there's a 2 on the top, so that just becomes sine 2 theta, and I'm done. And that's between minus pi and pi like that. As you can see, these questions are quite long. They take a long time. Hence why I've made one of the exercises optional. You might not get around to that. And one of them is compulsory. The one that's compulsory is doing these things. So, now we've got to work all that out. So, let's put the pi in first. So I've got 3 pi. Oh, I shouldn't be using it. I should be using curly brackets now. Sorry. Square bracket there. So 3 pi. Now sine of pi is 0. And sine of 2 pi is also 0. So I don't have to worry about those. Okay, now let's do the... so that's the first one. Now let's do the minus pi. So I'm going to get minus 3 pi when I put minus pi in there. And sine of minus pi is also 0. Okay, so I don't have to do anything with that. And sine of minus 2 pi is also 0. So the good news is that that's it really. And I end up with a heart. That doesn't, by the way, that doesn't always happen. I've gone wrong, haven't I? I've messed this up. Oh my goodness. Oh dearie, dearie me. Oh dearie, dearie me. Am I going to record a new video or are you going to let me off? So I've made a big mistake. I wonder if he spotted it ages ago and I've been watching this video, shouting, thinking, "Sir, you've messed it up. Can I put this right?" Oh, it's tricky. I don't want to have to record the whole video again. Oh, I'm going to put it right. I can't face recording another of these videos. Right, okay, so Sarah's messed up big time at this point. So, what's he gone wrong? Well, it's to do with this diagram here. It was never minus pi to pi, because remember, we had our dead zone here, between 2 pi over 3 and 4 pi over 3. Therefore, I should, or minus 2 pi over 3, I should say. So, what I should be doing is actually integrating between 0 and pi over 2. And then between 0 and minus pi over 2. Sorry, minus 2 pi over 3. So between 0 and 2 pi over 3 and between 0 and minus 2 pi over 3. So if I go back to my mistake, all I need to do to put it right, it's actually not too bad, is all of these should be minus 2 pi over 3 to 2 pi over 3. So if I go back through and change them all, talk amongst yourselves, it is now correct. Alright, so scribble that out. That's minus 2 pi over 3 and that's 2 pi, sorry, that's 2 pi, oh for God's sake, that's 2 pi over 3, that's minus 2 pi over 3. There we go, it's right now, and Sir is an idiot. Okay, let's continue on and get it right this time. So, it's just like being in a lesson, isn't it? Here we go. So it's a half. Open big brackets. Let's do the pi over 3 first. So, 3 pi over 3 is just pi. Here we go. Now, sine of pi over 3 is sine of 60 degrees, which is root 3 over 2. So, I'm going to write this as plus 4 root 3 over 2, like that. Okay, and then sine of 2 pi over 3 is sine of 120 degrees, which I believe is also root 3 over 2. Okay, but because I've had a wobble, I'm just going to double check that. There we go, root 3 over 2. So I've got another root 3 over 2 there, like that. Oh my God, I've gone wrong again, haven't I? Oh. This is getting serious now. Sorry, that one is root 3 over 2, and that one was sine 2 pi over 3. This one's going to be sine 4 pi over 3, which I think is going to be negative. Let's just check it. Sine of 4 pi over 3, which is sine of 240 degrees, is actually minus root 3 over 2. So that should be minus root 3 over 2. It's right now. So I'm going to take away from that the other one now. So this is now minus 2 pi over 3. There is a minus sign there, use your imagination. Okay, so minus 2 pi over 3. So this, oh that means, oh god, I just realised, that means that's 2 pi there as well. So minus 2 pi over 3 is going to be minus 2 pi. Okay, well we better check these, hadn't we? So this is sine of minus 120, which is minus root 3 over 2. So this is going to be minus 4 root 3 over 2. Okay, and then finally, the last one is going to, well, I can see what it's going to be already, but we'll just do it for safety. So this is sine of minus 240, which is root 3 over 2 as expected. So now I've got a plus root 3 over 2 there, like that. Okay, believe it or not, I'm pretty sure that all of that is correct. Believe that, you believe anything. Okay, so let's sort this out then. So we've got 2 pi minus minus 2 pi, which is 4 pi. And then we've got 4 root 3 over 2, minus one of them, which is 3 root 3 over 2. So 3 root 3 over 2. And then we're going to add to that 4 root 3 over 2, which is 7 root 3 over 2, and take one off, which is 6 root 3 over 2, which is 3 root 6 root 3 over 2, which is 3 root 3. Leading to a final answer of 2 pi plus 3 root 3 over 2. And that is, believe it or not, the area of that curve there, r equals 1 plus 2 cos theta. Don't believe me? Not sure I believe it myself. Put it into Wolfram. Put that curve into Wolfram Alpha and get it to find the, I think it will give you the area. Or alternatively, type it into Desmos and work out what the actual value of that is and then count the squares to see if it's right. I think it's right. I couldn't swear to it, but I think it's right. My method's right. I just messed up with the tangents here. So sorry about that. Hopefully you're still listening. It was a fun one today. 27 minutes long, that video. I'm going to stop there. Have a go at the exercise. Please ask questions if you get stuck. You might well get stuck. This is a topic I'd much rather be teaching you in school. But we'll just see how it goes. Just keep letting me know how you're getting on with that exercise, and we'll take it from there. Whew, that was fun. See you later.